Hydrogen has many uses in industry. Hydrogen is used for ammonia production, petroleum refining, methanol production, and many more aspects of industry. In the future, hydrogen could be used for space exploration, aviation, and hydrogen fuel cells. Hydrogen can also be extracted in many different ways. The typical process of producing hydrogen is through producing syngas by reacting hydrogen gas with steam, producing CO or CO2 as a byproduct. This is referred to as grey hydrogen. CO2 has a lot of beneficial uses. CO2 in a solid form, dry ice, can be used in cinemas and theatres and fog machines for a more immersive and less humid experience. CO2 can also be used in fire extinguishers and for the carbonation of soft drinks. It can also be used to produce biodegradable polymers. We look to base our factory in Germany. More on this topic is covered in the location section below.
We have chosen to locate the plant in Ludwigshafen, Germany, as it is located on the Rhine River and is the home of Germany's existing chemical manufacturing industry. This will mean that Ludwigshafen will have an abundance of existing infrastructure, for example, sound transport infrastructure, which can be taken advantage of to lower overhead costs. At present, the country is seeing massive investments into hydrogen technology to aid the net zero by 2050 ambition, 7 billion of which is directly from the government. The cost of hydrogen production using natural gas may also be lowered by the increase in diversification of Germany's natural gas supply due to the Nord Stream 2 project, the implementation of a new gas line from Russia to eastern Germany, and Shell commissioning the new liquid natural gas bunker barge in Barcelona. Despite the drawbacks of an increased cost of production, we expect this to be balanced out by the significantly larger increase in demand for hydrogen technologies.
Now we are considering the process description. By analyzing the material balance of the original process, we notice that the liquid water is generated in the flush drum. Meanwhile, the first reformer requires a large amount of steam for reactions. Therefore, for the first improvements, we develop a recycle step for water to reduce its usage for the whole process. It is returned to the previous process and mixed with the input natural gas. However, the recycled water is not sufficient in quantity, so we still need external steam to meet the reaction condition. Then the mixture will be preheated and flow into the reformer for reaction.
From the simulation of the energy balance around the first reactor, we notice that the process requires a lot of energy. This reminds us that we can reduce the energy cost by reducing the heat inflows. Since we have a heater and a cooler around, it is reasonable for us to put a heat exchanger between them. Therefore, for the second improvements, we add a double pipe heat exchanger. In a double heat exchanger, the hot flow enters the inner pipe and transfers heat to the cold flow in outer pipe. This allows thermal convection from the hot flow to the cold flow. We can further reduce the energy requirements if we add an isolation layer around the heat exchanger to reduce the energy lost.
From our research on the safety considerations for the production of hydrogen, there are two main hazards that we need to consider. These are chemical hazards and physical hazards. For example, chemical hazards can be due to exposure to toxic fumes, and physical hazards can be due to exposure to loud noises. The large-scale process for producing hydrogen requires the use of a variety of chemicals and large equipment. Therefore, it is important to follow the safety guidelines because failure to do so can lead to major incidents. Methane, nitrogen, and oxygen are some of the gases used in our system, and they are highly pressurized and they can be explosive. Therefore, it is important to monitor their pressure and store them safely. Also, hydrogen and oxygen are highly flammable, whereas carbon monoxide and hydrogen sulfide are toxic. Therefore, those on site must wear goggles, masks, and lab coats at all times.
A HAZOP is a qualitative risk management analysis method that seeks to eliminate or reduce the risk of hazards in the work environment and ensure there are not any operational procedures that may cause the plant to shut down and impact profits or violate safety regulations. When conducting our HAZOP, it became clear that the process requires a large amount of maintenance and periodic checks before operation. When dealing with such hazardous chemicals, it is vital that the system is checked for leaks, blockages, or broken valves. These can be immensely dangerous to the operation and could cause disaster if not found. In the event of a leak or blockage, the team would need to know exactly where it is coming from and what is wrong. To do so, thermal indicators, pressure gauges, and emergency exit outputs are required in order to immediately find and deal with the crisis. Sufficient training must be taken in order to safeguard the workers on site and the facility. It is of the utmost importance that all workers on site are operating maintenance checks and logging faults in the system as soon as they are reported.